Good afternoon.
Hello, nice to see you guys. How are you doing?
Good. Yeah.
Fine.
Good. So, just a reminder, tomorrow you have the midterm. So be prepared for that. During our last discussion, as a quick reminder, we introduced the concept of gravitational, like strengths of gravitational field and strengths of gravitational field. Also calculated the potential energy as a function of distance from the center of planet, for instance. And at the end of our discussion, we calculated total mechanical energy for satellite or planetary motion, which consists of two components, kinetic energy of this motion and potential energy of interaction via gravitational field. And have shown that this is for isolated system, which most of this sun, planet, or planet satellite systems is true. For isolated system, this total mechanical energy is conserved, so it remains constant, and that could be used for some useful approaches in terms of calculating different unknown parameters of this satellite or planetary motion. So today we will continue discussing gravity. This will be our last lecture on this topic, and we will focus actually during this discussion on escape velocity as important parameter, which defines how we can access outer space and leave the planet. And we will calculate this escape velocity in two different independent ways. So first we will go directly through a differential equation, and we'll get the expression for velocity of a projectile launched from the surface of the planet as a function of distance from this projectile to the center of the planet. Based on analysis of this equation, we will, applying some conditions, we will get the expression for the escape velocity. And afterwards, we will do the same calculation of the escape velocity. However, that will be we are applying the concept of conservation of total mechanical energy, and you will see that obviously it will be much easier and faster to do. However, it would be good for you to learn both options and see how we approach calculation of this parameter, which is escape velocity. Okay, so at this point, I think we can switch to the slides. And let's start with a direct calculation via a differential equation. So we have some planet with radius capital R and some capital M mass. At initial condition, our projectile had V initial velocity, then it moves, goes up. This like position with respect to the center of the planet will be given by radius like small r. And obviously this velocity of the object will be a function of this distance. It will change as the distance increases. So first goal is to determine this dependence, velocity as a function of distance. And second step will be to, based on this equation, to determine the escape velocity. So in order to do this, we need to consider the definition first. Let's start from the scratch of acceleration. It's first derivative of velocity over time. Also, we need to mention about second law of motion. So F is equal to m times a. In our case, this is isolated system, this planet projectile isolated system. There are no other forces acting on this system from outside. And here we have only gravitational force, which is equal to m times g as a function of r, where g is the strength of a gravitational field. As we discussed earlier, it is a function of distance from the center of the planet. So we can write for g that it's equal to minus g gravitational constant times mass of the planet divided by r squared, square of the distance from place where projectile is to the center of the planet. Minus here stands for the fact that gravitational force is attractive, so the gravitational field is pointed towards the center of the planet. So now we can define from one side this gravitational, so we can write that A, acceleration, is equal to strength of gravitational field, because on the surface of the planet, this G is this known kind of constant which we use, 9.8 is acceleration of free fall. So we can write that dv over dt is equal to minus g gravitational constant times mass of the planet divided by r squared. So there is a problem here because we need to we want to get not velocity as a function of time, we want to get velocity as a function of distance. So we need somehow to get rid of this time here in this expression. And the way how we can approach this will be dv over dt. Let us multiply it by dr and divide by dr. So nothing changes because that's actually unity, but it will help us to rearrange the this left side of the equation in the way we want. So any ideas? How do we get rid of time here?
dr by dt equals velocity.
Okay, that's good. Here we will have dv over dr and dr over dt. And that will be v, velocity, times dv over dr. Okay, so we have already accomplished this task and got rid from the time in the left side of this equation. So let's write our result here. V times dV over dr is equal to minus G times M over R squared. So now we rearrange variables. Will be V times dV is equal to minus Gm times dr divided by r squared. So now we have this simple differential equation. We need to integrate it in order to solve this equation. Gm goes out from the integral because these are constants, they don't change with distance. Okay, so let's integrate and see what we get. So V squared divided by 2 is equal to minus G times mass of the planet times minus 1 over R. And we don't forget about the constant of integration. So obviously, in order to get the expression, final expression, we need to determine this constant of integration. For that purpose, we need to use certain boundary condition. Any ideas which boundary condition we need to use here? What will be convenient for us?
Maybe initial height and final height.
We don't know. We know initial. Yeah, that's good starting point. We know initial distance from the center of the planet. It starts on the surface of the planet. So initial distance will be r. So let's consider that small r is equal to capital R. But here we need to final distance. So we need to decide, we consider final or initial. So we consider initial distance. But then we need one more. So at distance, which is equal to radius, yeah, infinity is final, but that will be, so we need to pick up one distance, either initial or final, and one corresponding another parameter, which is from the left side. From the left side, we have V. So at initial condition, when we start from the surface, launch this projectile from the surface of the Earth, velocity V is equal to initial velocity, V initial. So we can write here V initial. So these are our boundary conditions. We can apply them and determine the constant of integration. So let us do it on the next slide. So what is here? Oops. What is here? V squared. Okay. V squared divided by, actually, we can already apply this boundary condition. Vi squared, V initial square divided by 2 will be equal to and also we need to keep in mind that here we have minus and minus that will give us plus. So it will be G mass of the planet divided, instead of small r, we put here capital R, which is radius of the planet, plus constant. So from here, we can write that the constant of integration for our case is 1/2 V initial square minus G times capital M mass of the planet divided by its radius. Okay, so we already managed to determine this unknown constant of integration. Let us substitute it in the equation. So we had V squared divided by 2 is equal to GM divided by small r. Then we need to write the constant here. So it will be plus 1/2 of V initial square minus GM divided by radius of the planet. So now let us rearrange this. It will be 1/2 V initial square minus gravitational constant times mass of the planet times 1 over radius of the planet minus 1 over distance from the to the center of the planet. Okay, so we can now express V velocity as a function of distance of the projectile to the center of the planet. So that will be equal to square root of V initial square minus 2 G times mass of the planet 1 over R minus 1 over R small. Okay, so first step we accomplished. We have this expression for velocity as a function of distance. And now we need to consider conditions at which the projectile will leave the planet and like escape from the gravitational field of the planet and will never come back to the surface of the planet. So for that purpose, this velocity at any distance should be always larger or equal to 0. It cannot become negative, because if it becomes negative, it means that it will just fall back on the surface of the planet. So in order to set this condition that it will escape the gravitational field, it should be positive or equal to 0. From other side, we know that it will escape from the gravitational field when it goes so far from the center of the planet that this R will approach infinity. And automatically means that 1 over R, which is here, will approach 0. So we can cancel this part, 1 over R, and consider that in order to satisfy this condition, the argument under the square root should also be larger or equal to 0. So V initial square minus 2G times mass of the planet divided by R. So we cancel with this 1 over R small, should be larger or equal to 0. So let us consider the case when like the minimum escape, the minimum velocity, which will be the required to escape the gravitational field, which is called escape velocity. Then we can write from here that V initial, which is required to be provided to the projectile in order to escape the gravitational field of the planet, will be equal to square root of 2g times mass of the planet divided by its radius. So that is the equation which gives us the opportunity to calculate the escape velocity for any planet if we know the mass of the planet and its radius. This was done based on differential equation, deriving equation, which relates the velocity and distance from the center of the planet, and setting initial conditions, assuming that the projectile starts its motion from the surface of the planet with certain initial velocity. So now let us do the same, means the same derives this equation for escape velocity, which you kind of try to remember. So we will compare later by applying the concept of conservation of mechanical energy. So we have similar, like the same situation. We have a planet, a projectile with initial velocity. Here is the radius of the planet and mass of the planet. So what do we have initially? We have both kinetic and potential energy of this projectile. So we have 1/1/2 times mass of the projectile times initial velocity square. That is term responsible for the initial kinetic energy minus, as we derived and discussed during previous lecture, potential energy associated with the gravitational field. So here we have gravitational constant times mass of the planet times mass of the projectile divided by radius of the planet, because initial position is on the surface, so R capital, radius of the planet, will define the distance from the projectile to the center of the planet. Then at some height, h, velocity will be equal to 0. So it will give all kinetic energy in terms of overcome this gravitational force, which attracts the projectile back to the surface of the planet, and at some height it will reach 0 velocity. So let's consider this case, and in that case we will not have any kinetic energy because velocity is equal to 0, but there will be some potential energy. And potential energy we can express as minus gravitational constant times mass of the planet times mass of the projectile divided by, let's call it R maximum. It will be maximum distance from the center of the planet. So it will be something R maximum is equal to R capital, radius of the planet, plus this height h with respect to the surface of the planet. So here we can cancel out this mass of the projectile and or express the initial velocity as the function of other parameters involved in this equation. So 2 times g times mass of the planet, 1 over radius of the planet, minus 1 over R maximum. Now we assume also condition that it will escape the gravitational field of the planet if R maximum approaches infinity. So 1 over R maximum will be equal to 0. And from here we get V initial square is equal to 2g times mass of the planet divided by radius of the planet. And as a result, we get expression for the initial velocity required to be provided to the projectile to escape the gravitational field of the planet, which will be square root of 2 times gravitational constant times mass of the planet divided by its radius. So you see that we got the same expression for escape velocity as the previous one, which we got based on the solution of a differential equation. Here it's much simpler, and that's why this concept of conservation of total mechanical energy in the case of satellite or planetary motion is really very useful and can be applied for different cases. So with this, I would like to, at this point, give you some examples of values of this escape velocities. For instance, for planet Earth, escape velocity is something like 11.2 kilometers per second. For our moon, it will be 2.3 kilometers per second, much smaller because the weight, the mass of the moon is much smaller. And for instance, if we consider the biggest and most massive planet of our solar system, which is Jupiter, that will be 60 kilometers per second. So it's quite huge escape velocity. And if you think, just imagine such situation when it's like unlikely, but of course, let us imagine such a situation that our planet is comparable, possess comparable mass of the mass of Jupiter, and this escape velocity for our planet would be 60 kilometers per second. That means that our currently used technology for going to the space would not work because of its limits. This propulsion motion with currently available chemical fuel would not just develop such force in order to reach velocities required to escape the planet. So we would not have an opportunity to send any satellites to outer space and do the space exploration. So that's kind of interesting moment, that this mass of the planet Earth is not too big, so big enough to keep the atmosphere, not allow it to be blown away, but not too big to stop our efforts and possibilities to send satellites to outer space. Of course, planets are not the most massive objects in the universe, and if we consider stars, for instance, depends on the initial mass of the star. It will be defined how the evolution of the star will happen, will go on. So there is a very rough estimation that if the mass of the star is smaller than 1.4 mass of our sun, then over time of burning this hydrogen, as thermonuclear fuel, like fuel for thermonuclear reactions in the core of the star, as a result of this fusion, helium atoms, like helium nuclei, alpha particles are produced, and that results in burning the fuel. So eventually there will be some white dwarf star, which will slowly cool down. However, if mass, so that is the future of our sun, since obviously mass of the sun is 1.0 mass of the sun, it's smaller than 1.4. And if mass is larger than 1.4, there is a chance for supernova explosion in the end of existence of the star. And this huge pressure which creates during the explosion of supernova causes the densification of the core material, so which is so extreme that it initiates neutronization of the matter. Literally, protons fall on, so electrons fall on protons and convert them to neutrons. So the so-called neutron star is formed, which possesses the density of the core of atom and consists literally from neutrons. Such matter is of extreme density, and definitely it creates very strong gravitational field around itself. So the escape velocity depends on the size of this neutron star, will be insanely large. However, if initial mass of the star is more than 3 masses of the sun, that could be so much of pressure that the black hole is formed. So in this case, the escape velocity will become literally more than speed of light. And since we cannot reach any signal transfer with higher speed than speed of light, it's a universal constant, and the highest possible speed of transferring any signals, including photons, like quants of light. So in this case, if photons go into a sphere around the black hole, which is defined as event horizon, then it cannot come back because this interaction with gravitational field of black hole is too high. So escape velocity is literally larger than speed of light. So that's some extreme condition which can be observed in universe. Recently, we got direct observation and visualization of the black hole a few years ago, which is really a remarkable achievement, applying this radio telescopes. And the fact that our planet is not the black hole yet, and the black holes are not around our planet in close proximity, that means that we have good time and ability to explore universe for longer. So this is pretty much everything what I wanted to tell you about gravity. And if you have any questions, you're welcome. Keep in mind that tomorrow you have the midterm. Be attentive, read the problems first carefully, define those problems which are simple, solve them, and then try to deal with problems of higher complexity. So it will secure your that minimum score which can be achieved. At least you will not lose this part. There are 6 problems. You can get all detailed information described in this letter, which I sent, like reminder email sent to you. There is also a link to this Google Drive, a Google folder, where the solutions will be provided afterwards, after the exam. So I wish you good luck, and be careful, don't mess up with long kappa. That's another source of problems. Please submit in the correct format with correct units, and everything should be okay. And
Thank you very much.
Yeah, and see you already after the fall break, because we have this fall break 1 week. Our lectures will start after, like in a week, on Monday.
Thank you. Bye.
Okay,
See
bye
you.
bye.
Thank you.
Goodbye.
Goodbye.
Have a good
Thank you. Goodbye.
vacation and relax a bit.